Okay, welcome everybody. We've been talking about functional programming on Channel 9 an awful lot. I hope you enjoyed all the conversations we had with Brian Beckman, Don Syme, Andrew Kennedy, with me, with Wes. You know, functional programming is a hot topic these days, but really we never gave you an introduction to the fundamentals of functional programming. So as an experiment, what we're going to do is I'm going to go and do a lecture series based on my favorite functional programming book, Programming in Haskell by Graham Hutton. And so for the next couple of weeks, I'll go through each chapter of that book and present you a lecture on that. And in that way, I hope that you get a better understanding of what's underneath functional programming and why we are so excited about it. So let's jump right in chapter 1 of Programming in Haskell. So the thing that functional programmers usually use to pitch the importance of functional programming is that it solves the software crisis. So they use the typical marketing by fear approach. And they say, oh, programs are getting big and complex. And how do we make sure that programs are correct on the one hand, and how can we make it cheaper to develop code? And of course, this is a real problem. As everybody knows, programming is hard. So I'm not so sure that there's really a crisis. It's just because programming is intrinsically hard. And so we need to have tools to make our lives easier as programmers. And now the functional programming guys are saying, oh, we can solve the software crisis by having a really great language. And, what they will say is like, this language will allow you to do formal verification, it will allow you to write reusable components, and it allows you to write code at a high level of abstraction. Now really, if you look at this is a very generic pitch. Because you can fill in here for object-oriented programming as well. Right? This is not specific to functional programming. If you read literature about object-oriented programming, well, objects allow you to write code at a high level of abstraction because you can model the real world. There's a reuse, the whole .NET framework is all about reuse. And then, of course, we have spec sharp, code contracts that are also help you to write code with formal verification. So none of these things is specific to functional programming, but functional programming has some unique features. And that's what's said here is functional programming, in particular pure or fundamentalist functional programming, is like a petri dish. Simon Peyton-Jones uses that term. Pure functional programming is like a petri dish in which you can experiment with all these things in a very lightweight way. And then what happens is that a lot of these ideas from pure functional programming find their way in more mainstream languages, or we see more hybrid languages like F# or OCaml, or even C# and VB appear that take over these ideas that were developed in the context of pure functional programming. But that's, I think, why it's important to really understand where this all comes from. I'll put the book away. Because, it's always good to go back to the source. So, then what is a functional language? And I've talked about this a lot. And I have a slightly different opinion than Graham here. A lot of people say functional programming is a style of programming. So it's a style where, you're working in an expression-oriented way, and you're passing around, closures or Lambda expressions. And that's an okay definition, but I think, I really like the notion of functional programming where you're programming with mathematical functions and not with something that supports a functional style, because that doesn't make a sharp enough distinction. And so, because even object-oriented programming, if you're doing fluent interfaces and so on, is about, programming in more expression-based style. And what's unique about Haskell is that it really allows you to program with mathematical functions. And now, I'm not saying that that's kind of a practical way of programming, but again, by being forced to not cheat, you know, you're forced to get clarity. And then you can use these ideas again and transfer them to do a functional style. But I think it's very important to distinguish a functional style from a fundamentalist or a pure functional language. So let's look at the first example where, you know, we contrast the kind of functional style with the imperative style. And you know, this is pseudo Java because, you know, it's not, it won't even type check or compile, but you get the idea. So the thing is that in a normal kind of imperative style, you write a loop with, you know, an assignment function here, and it's very stateful. So it's very imperative. You know, you really tell the computer, you know, go to this loop and now add to this kind of counter, you know, add the value to it. And you see here also what's important is that since this is a statement, there is no resulting value. So, you know, you store the result of this computation in this local variable. But the computation itself, you know, is not a first-class thing that I can pass around. I cannot, you know, call another method, you know, and pass it this thing, because I now have to do this and then call a method passing total. So you see that, you know, your code gets fragmented. It doesn't kind of flow very nice. So here's how you would write the same code in Haskell and F# or other kind of functional languages that have these kind of range expressions, or even Python. It will look very similar. And what you do there is you kind of separate the kind of, you know, generation of the loop from the summation. So it's like very much divide and conquer. So I write, you know, first create a list that has the elements from 1 to 10, and then I sum it. So you see that it's a much more compositional style, whereas this is a monolithic program that's kind of, you know, well, composed out of statements, whereas this is something that's composed out of expressions. And the nice thing about expressions, and we will say later too, how that kind of the program experience kind of supports it, is that you can kind of verify each of these expressions individually. I think that's the main advantage of functional programming or pure functional programming, is that each sub-expression is independent of its context. So you can test it and look at it and understand it by itself and then compose it together. Which, you know, if we go back to this thing here, I cannot just look at this you know, statement here, total equals total plus I, in isolation, because, you know, it has all kind of, you know, ties to its environment, which makes it much harder to reason about for you know, humans, because, you know, there's like, you know, tentacles everywhere. All right. So it's also you know, very good to kind of look a little bit at history. In Dutch PhD thesis, you know, one of the traditions is that you have like a list of statements, you know, and that comes from the Middle Ages, where the real PhD thesis was, you know, you had your thesis, and then, you know, you would prove that in the written up kind of part. And that now we were just kind of making jokes. And one of the kind of statements I had in my thesis was, computer scientists do not know their history. And that's often the case. We think that everything is new in our field. But in reality, most things are really old, and they were invented or discovered by mathematicians. And the same with functional programming. So the functional programming or the Lambda calculus, you know, that's where the notion of Lambda expressions in C# and VB and F# and Haskell comes from, was invented by Alonzo Church in the 1930s. So that's kind of, you know, a long, long time ago. And what you see also is that, you know, it takes a long time for these inventions to, you know, to reach the mainstream. It's like, you know, when you buy some expensive bottle of water, right? It says, oh, it took 150 years for the rain to percolate down the mountains, like deep, you know, wells and whatever. And it's the same here. So mathematics is a very good source of ideas, and usually, you know, it takes like 150 years or something, you know, to reach the mainstream. Then in the 50s, you know, Lisp really, you know, was one of the oldest programming languages, and that was directly inspired by the Lambda calculus, but you can already see that in Lisp there was already mutable state involved. And that's very tempting because our machines, the von Neumann machines, are all based on, you know, mutable state. That's or even Turing machines, right? It's all, that's the kind of, you know, the essence of our computational model. And so it's no surprise that especially in the early languages, you know, people kind of borrowed ideas from the Lambda calculus, but also that the kind of underlying machine model kind of shines through in that language. And then Peter Landon, he just died, and there's, you know, if you now go to the web, Olivier Danvy has a very nice kind of, you know, talk that you know, explains the importance of Peter Landon on our field. And one of the things that he did was like working on a language called ISWIM, if you know, you see what I mean. And this was the first purely functional language. And this is a very, very interesting language because it also has the offside rule that's now in Python and in Haskell. And another thing is my favorite paper of all times is written by Peter Landon, and it's called The Next 700 Programming Languages, and he kind of describes the idea of domain-specific languages in there. So, you know, a lot of people think, oh, domain-specific languages, that's the hot topic of today. Well, again, that was, you know, invented in the 1960s in the context of functional programming. But the great thing here was that he showed that you can, you know, build programming languages that have absolutely no assignments, using only pure functions. And in the same kind of era, in the same time, people were discovering, Dana Scott and Strachey were discovering denotational semantics, where they kind of show how you can define what an imperative program means by kind of, you know, writing an interpreter or translating it into a pure functional language. So that's kind of really groundbreaking work. And that's also where the idea of domain-specific languages comes from, because you can define the semantics of your domain-specific language in a pure functional language. So the functional language is like the host language for the embedded DSL. And then, if we go a little bit more to recent history, John Backus, he also left us, I think, a couple of years ago, developed an interesting language called FP, and that emphasized, you know, higher order functions and reasoning about programs. And if you go and look, you know, online on Wikipedia, or you search for articles on FP, one of the interesting things that John Backus did with FP is to try to write code in a kind of variable-free style. So he really, you know, a lot of these things are like a real composition of kind of, you know, little functions. And that style is what you really now see in LINQ. If you look at LINQ, we have like the standard sequence operators like where, select many, group by. And what you do is you write your programs by kind of chaining together these functions that kind of transform their input streams into the output streams, and you just stack them together in a long sequence. And that was kind of, you know, what FP also tried to do. And if you write your code in that style, now you can kind of transform. So if you have like x's.where p.where q, you can transform that into x's.where p and q. And those are kind of, you know, the kind of things that Backus talked about. I think in practice, you're writing your code in this point-free style, as it's called. It is quite hard. But again, it's an inspiration, and you see the influence directly on our mainstream languages like C# and VB. So that's cool. And of course, F#. In F#, if you use F#, often you use this kind of thing, you know, the operator, what is it, with the triangle that does kind of, you know, chaining of function calls. That's very, very much in the John Backus FP style. And then another very important influence on the field is Robin Milner, who and others, you know, that, and in some sense a lot of this stuff comes from Great Britain. That's also interesting, but we should probably talk about that in a different context why that is the case. But Robin Milner worked on ML, and the nice thing about ML is that was, you know, a place where type inference and generics or polymorphic types kind of showed up. So, you know, so generics is, again, it's like an old invention that finally now has found its way in more modern languages. But, you know, Eiffel had, you know, generics for a long time. But for example, you know, I couldn't live without type inference in C#, so I use the var keyword all the time, because why would I write something down when the compiler can infer it for me? And so these people like, you know, Robin Milner first experimented with these things, and again, coming from a very mathematical background. One of the you know, the goals of ML was as a scripting language. It was a scripting language to script proofs, formal proofs. So also the idea of scripting languages, you know, that's now another hot thing, was, you know, prototyped and experimented first in this kind of, you know, context of, you know, more theoretical, mathematical, functional programming. So you see the influence of functional programming is immense on the field. All these things that people thought about, you know, many decades ago now show up, and everybody takes them for granted. But I think it's really good to kind of realize where it came from. And I tell you, there's a lot of stuff still there that we can harvest into our languages. So it's, as we say in Dutch, it's always better to steal a good idea than to, you know, have your own bad ideas. And there's still, I think there's still a lot of good ideas in the kind of, you know, in the old functional programming and old math literature. And then this is really David Turner. He's my hero because when I was in college, and people may have heard the story, but when I was in college, I was completely bored. So I kind of, you know, ended up hacking, trying to kind of, you know, not the good kind of hacking, but the bad kind of hacking, trying to kind of, you know, break into the mainframes and stuff like that. And then one professor, Raymond Boete, kind of, you know, called me into his office and he said, Erik, you know, here's like a paper, you know, on Cecil, which is the precursor of Miranda, and here's like a flyer about the Japanese 5th generation project on Prolog. So I was saved from, you know, going to the bad side by functional programming, and I got completely hooked on David Turner's languages. So his first language was Cecil. Cecil was an untyped purely functional lazy language that was directly based on ISWEM. So it had offside rule and everything. And the interesting thing about Cecil was that it was completely untyped and that it was compiled into what people call the combinator. So it you can show, and I would really recommend people to kind of, you know, look it up, is you can take a functional program, a purely functional programming, and compile it into only 3 functions, S, K, and I. I should write that down. So there's S, K, and I. So I can take any program, you know, that's some expression here, and I can compile it into these 3 functions. And that's quite remarkable. And you know, let's see if I can remember what they are. So I is the identity function. K is the constant function. And I always forget which direction it goes. Doesn't matter. But you can look that up on Wikipedia. And then here, I think S is it takes, you know, an argument and kind of distributes it kind of, you know, over. So it's kind of lifting the application and kind of passing an argument down. So I think this one is like this, x, y, x. So this is the kind of idea. So intuitively, operationally, so if you have a function And what is a function? Well, you can apply a function to an argument. And now, what does application mean? Well, I have to take that argument and kind of route it in that expression to the places where that argument is used. And that's exactly what these three functions do. It's like the identity function says, if you have an argument, well, I use it here. The constant one says, well, if you pass me something, I just throw it away, and it will return the value that was there. And this guy takes, if there's like a branch, an application, it will just distribute the argument to the left and to the right. So intuitively, you can understand how you can take any function, any lambda, so it's like lambda x e of x. So if I have a lambda expression that, used on x, I can replace this e by a more complicated expression of these sk and i's that just kind of routes these arguments down. And that's kind of very fascinating. And even you don't need three. So you can show, Jeroen Fokker has a nice paper about it, you only need one of these combinators. So you can take any lambda expression and compile it into a single instruction. And that's kind of beautiful. So now, why did I kind of went through this long excursion to talk about SKI combinators? Well, the thing about Cecil was that it was an untyped language. And so that meant the compiler would not catch certain errors. So often when you made an error, you would get a runtime exception, and then the error message that you would get is would say cannot execute, and then you would get kind of a giant expression using this sk and I. It's like your stack trace. It says I was trying to kind of evaluate this super complicated thing with sk and I operators, and I cannot evaluate that. So that was kind of interesting, but it's also it's like you've often felt that these errors were avoidable. So often what would happen is you would kind of have a list of lists, but really you were expecting a list of lists, but you were passing only a list, and so on. And so one of the great things that David Turner did with Miranda was to add types to a lazy functional programming. And again, that was already done in ML, type inference and algebraic data types. But ML is a strict language that also has side effects. It has you can have mutable variables. By the way, ML is the direct precursor of F#, because ML, OCaml, ML, and then F# came from that. What Turner did is he would use this lazy and pure functional language, and then he added the ideas of type inference and algebraic data types, and suddenly, all these kind of weird errors that you would experience in this untyped language would disappear, and the compiler would tell you. And I think, from that time on, I've become, a big fan of static typing, because, I like the compiler to kind of, find my errors. But on the other hand, the type systems can get really complicated because, you're trying to kind of, let the compiler do more and more and more. So sometimes, you want to have kind of an escape hatch where you want to say, okay, forget about it, I'm going to do something kind of dynamic. And that's what I wrote about in my paper about static typing where possible, dynamic typing where necessary. And again, I think this whole, interplay between static and dynamic typing has its, background in functional programming as well. Another good example of a dynamically typed language is Scheme, which is, again, a successor of Lisp. Scheme traditionally is dynamically typed, but if you look at kind of the latest developments in the Scheme world, they're trying to add types and contracts to Scheme. So there's a very kind of interesting developments where we're trying to mix dynamic and static typing, and again, all of that directly related and inspired by functional programming. Then not too long ago, or although not too long ago, that's like, you know, more than 20 years ago. I cannot believe it. I feel old. Well, you can see it, everybody, that I'm getting old. But Haskell was the idea of, you know, the functional programming community to define a standard, lazy, purely functional language that people could use to kind of, you know, experiment. So the idea was, if we would share kind of one language, then, you know, because at that time there was like a whole explosion of languages. If we would have like a central language, then we can kind of, you know, we don't have to implement everything ourselves, and it would become easier to do experiments and research based on that language. And I think Haskell has been a kind of, you know, tremendous success, and it has spawned off a lot of interesting research. And again, Haskell has directly inspired things like LINQ and C# and, you know, even in F#. The lightweight syntax in F# is kind of, you know, inspired by the Haskell syntax. So I think Haskell is kind of, you know, another functional language that has a tremendous influence. Even if not that many people program in Haskell, it's still, you know, it's not, you know, the fact that you program in Haskell, but the influence in Haskell on other languages is probably much more important. You know, after kind of a lot of changes and growth, in 98, the standard was defined, Haskell 98, and, you know, I can recommend this book to everybody too. It's, you know, that's a kind of revised report. In Haskell, it's like the C# language spec or the Java language spec, and I think it's always good, if you really want to understand a language, to kind of look at its kind of definition. It's very precise. It's not mathematical. The standard ML definition is also interesting, because that's really formally defined. This is more defined in the style of the C# language specification and the Java language specification. And nowadays there's a couple of Haskell implementations. There's GHC, there's Hugs, then there's one from York. So there's a kind of, you know, a couple of Haskell specifications that all, you know, implement the Haskell 98 standard plus extensions. So let's look at a kind of, you know, a program in Haskell. And again, it's not so much about Haskell, but what I really want to emphasize in this lecture series is pure lazy functional programming. And we need to have some syntax and some concrete you know, example of a language. So that's where we use Haskell for. But again, it's about functional programming, not about Haskell per se. And then, you know, the idea is that you can use these ideas in your daily programming, and you can see how ideas from pure functional programming have influenced languages like F# or C# or VB or Java or Python or Ruby, whatever your favorite language is. So this is a kind of, you know, example that a lot of people use in Haskell, and, you know, the question is, what does this do? Well, this is quicksort. Quicksort expressed in Haskell. And some people argue this is not really quicksort, because, you know, an essence of quicksort is that it's in situ, that it kind of, you know, takes an array and kind of updates the array in place. On the other hand, if you want to understand the algorithm kind of behind quicksort, then this is a kind of, you know, fabulous description. Because here is how it goes. If you want to sort the empty list, well, that's already sorted. Now if you want to sort a list, you know, that starts with x and has x's, what you do is, I'm going to split that list into things that are smaller than x. So give me all the values in that list, in the remaining list, that are smaller than, you know, that first element. Give me all the elements that are larger than that element, and I just then glue it together, all the elements that are smaller, the element that, you know, I use to kind of discriminate, and then the elements that are bigger. So here you see that in very concise, you can see the kind of, you know, the essence of quicksort. And then, of course, if you want to do an efficient implementation, you write imperative program that kind of, you know, does this all in place. But this program allows you to really understand what's kind of going on. What is the main idea behind quicksort? And I don't think, you know, There's many languages in which you can write that in this kind of concise way. Now, of course, in C# with LINQ, you know, what LINQ comprehensions are really just another syntax for this. So now in LINQ, in C# you could write something similar like this too, except that you cannot do this kind of pattern matching. And that's something that, you know, functional languages you know, have, and that's a very, you know, prominent feature. You see that in F# as well, where you're doing this kind of case analysis over your input values using pattern matching. But you can get around that, you know, with, without pattern matching as well. So it would be nice kind of homework to try to write this quicksort using comprehensions in C# or VB. And you know, you might find some old blog post of mine when I was still blogging that kind of does exactly that. So if you want to cheat, you can find the solution on the web. All right, so this was the first lecture. I left you with a little homework. But you know, if you have any questions about the lecture, anything, just, you know, put them in the discussion, you know, on channel 9, and then in my next lecture I will address them. So so far so good. I hope that you enjoyed the first installment of the lecture series, and hope to see you all next time. Thanks a lot.